Hello friends, welcome back to my channel. Today I would like to talk on the topic analytical techniques, mass spectrometry. The main use of mass spectrometry is in the identification of organic compounds. The mass spectrum of an element can be used to measure relative isotopic masses and their relative abundances. This information is used to calculate relative atomic masses. Determination of AR from mass spectra. A mass spectrometer can be used to measure the mass of each isotope present in an element. It also compares how much of each isotope is present, the relative abundance, otherwise relative isotopic abundance. We can use the data obtained from a mass spectrometer to calculate the relative atomic mass of an element very accurately. To calculate the relative atomic mass, we follow this method. Multiply each isotopic mass by its percentage abundance, add the figures together, divide by 100. We can use this method to calculate the relative atomic mass of neon from its mass spectrum shown below. The mass spectrum of neon has 3 peaks. As you can see here, AR of neon equals 20 times 90.9 plus 21 times 0.3 plus 22 times 8.8 over 100, which is equal to 20.2. Identification of a substance. As in other forms of spectroscopy, a substance can be identified by matching its spectrum against a spectra of known substances stored in a database. This technique is known as fingerprinting. The molecules in the small sample are bombarded with high-energy electrons, which can cause the molecule to lose an electron. This results in the formation of a positively charged molecular ion with one unpaired electron. One of the electrons in the pair has been removed by the beam of electrons. As you can see here, the electron bombardment of a molecule gives rise to a molecular ion. The molecular ion can further fragment to form new ions, molecules, and radicals. Figure below shows the mass spectrum produced by propanol. The peak at the highest mass to charge ratio is caused by the molecular ion. It gives us the relative molecular mass of the sample. We can assume the ions detected carry a single positive charge, so the reading on the horizontal axis gives us the mass. In the case of propanol, CH3COCH3, the molecular ion has a relative mass of 58. This corresponds to CH3COCH3 plus with a mass of 3 times 12 plus 1 times 16 plus 6 times 1. We also get large peaks at 15 and 43 on the mass spectrum. These peaks are due to fragments that are produced when propanol molecules are broken apart by the electron bombardment. Knowing the structure of propanol, we should be able to identify the fragment responsible for each peak. The fragmentation of propanol, CH3 plus causes a peak at 15 and CH3CO plus causes a peak at 43. The electron bombardment has caused the CC single bonds in the propanol molecules to break. This has resulted in the fragments at M by E 15 and 43 that are observed in the figure. The breaking of single bonds such as C single C, C single O, or C single N is the most common cause of fragmentation. These are the common fragments in the mass spectra of organic compounds. 15 is produced by CH3 plus, 28 is by CO plus or C2H4 plus, 29 is by CH3CH2 plus, 43 is by C3H7 plus or CH3CO plus. High resolution mass spectra. High resolution mass spectrometers can distinguish between the ions that appear to have the same mass on a low resolution mass spectrum. Table below shows the accurate relative isotopic masses of the most common atoms found in organic molecules. Isotope and its relative mass is given over here for hydrogen, carbon, nitrogen, and oxygen. These accurate isotopic masses allow us to measure the mass of the molecular ion so accurately that it can only correspond to one possible molecular formula. For example, a molecular ion peak at 45 could be caused by C2H7N or CH3NO. However, a high-resolution mass spectrum would show the C2H7N plus peak at 45.057846 and the CH3NO plus peak at 45.021462. We can therefore be sure which molecule is being analyzed. Using the M plus 1 peak, there will always be a very small peak just beyond the molecular ion peak at a mass of M plus 1. This is caused by molecules in which one of the carbon atoms is the carbon-13 isotope. This is shown in the mass spectrum of ethanol in the figure below. In any organic compound, there will be 1.1% of carbon-13. We can use this fact to work out the number of carbon atoms N in a molecule. We apply the equation N equals 100 over 1.1 times abundance of M plus 1 ion by abundance of M ion. Example question. An unknown compound has a molecular ion peak M plus with a relative abundance of 54.5% and has an M plus 1 peak with a relative abundance of 3.6%. How many carbon atoms does the unknown compound contain? Substituting the values of relative abundances into the equation, we get N equals 100 times 3.6 over 1.1 times 54.5. That will give you 6. That means there are 6 carbon atoms in each molecule. Using M plus 2 peaks, if the sample compound contains chlorine or bromine atoms, we also get peaks beyond the molecular ion peak because of isotopes of chlorine and bromine. Chlorine has 2 isotopes, chlorine 35 and chlorine 37, as does bromine, bromine 79 and bromine 81. Table below shows the approximate percentage of each isotope in naturally occurring samples. Chlorine 35, as you can see, 75%. Chlorine 37, 25%. Bromine 79 is 50% and bromine 81 is also 50%. Imagine a sample of chloromethane CH3Cl. We will have molecules of CH3Cl with 35, which is 75%, and molecules of CH3Cl which has a mass of 37, which is 25%. The molecular ion will be CH3Cl35 plus, and 2 units beyond that on the mass spectrum will be the peak for CH3Cl37 plus. The peak for CH3Cl37 plus will be 1/3 the height of the molecular ion. This is the M plus 2 peak. In the mass spectrum of bromoethane CH3Br, we will have 2 molecular ion peaks of approximately the same height, one for CH3Br79 plus and the other for CH3Br81 plus, which is the M plus 2 peak. You should look out for the relative heights when interpreting mass spectra. If the M plus 2 peak is 1/3 the height of M peak, this suggests the presence of 1 chlorine atom per molecule. If the M plus 2 peak is the same height as that of the M peak, this suggests the presence of 1 bromine atom per molecule. Here, a mass spectrum of chlorobenzene with M plus 2 peak is shown. And that's all. Thank you so much for watching this video.